Hi, everyone, and welcome to Module 10, Lesson 1, where we're going to begin our conversation on equilibrium. So equilibrium occurs when the rate of the forward reaction equals the rate of the reverse reaction. Once equilibrium is reached, the rate of reactants being produced is equal to the rate of products being produced. So in equilibrium, something that's super important to understand is that we are now seeing a double-sided arrow. A lot of the times I just write it like this so I don't have to, it just saves me time. So we've got a double-sided arrow, and what it means by the rate of the forward reaction equals the rate of the reverse reaction. So in an equilibrium, when a system is at equilibrium, products are being made at the same rate as reactants are being made. So there's a forward and a reverse going on at the same time, but it appears as if all of the reactants and products are constant. So what does that look like in a graph? So red will be the reactants, and so I'm going to start with reactants, and then over time, the amount of reactants will decrease and then flatten out because it becomes constant. Now the blue would be products. Products, I'll start with none, obviously. And those are going to increase until eventually they will also flatten. Now, the equilibrium position is reached when these lines become parallel to each other. So about at this time, this would be where equilibrium is established. The equilibrium position is the concentrations or gas pressures established at equilibrium. And again, it doesn't have to have equal amounts. You could also see a graph that looks like this. Okay, so the whole idea is that reactants are decreasing until it becomes flat. Products are increasing until it becomes flat. So equilibrium constant expression, this is one of the couple things that you have to be able to do with this, is the ratio of products to reactants at equilibrium. The higher the number, the more products are made. The smaller the number, the more reactants remain. To write an equilibrium expression for the following equation, so we got our equation right there. The equilibrium constant expression is equal to the concentration of products raised to their coefficients divided by the concentration of reactants raised to their coefficients. Only aqueous solutions and gases are included in your equilibrium. Do not include pure solids or liquids. Okay, so if I was to use that equation here, my equilibrium expression would look like this. So the coefficients are the lowercase letters. So I'm doing products raised to their coefficients divided by reactants raised to their coefficients. And that's what it would be, assuming all of those are either liquids or, are either solutions or gases. So again, one thing you're going to have to be able to do is to write out an expression and then actually solve the value of one. And you're also going to have to be like, well, what does this mean to me? So what does the equilibrium expression tell me? Since these are reversible reactions, they can either be going in the forward direction or reverse direction. If K is greater than 1, the reaction favors the products, and if K is less than 1, the reaction favors the reactants. So let's write out some of the expressions for these two. I know there's a third one, but it's not balanced correctly, and I did not have the patience to do it. So we're just going to do the first two because once you see how it's done the same way every time. So in this first equation, you'll notice everything's a gas, so I don't have to leave anything out. So I can just write my KQ is going to be equal to the concentration of the nitrogen times the concentration of the hydrogen. We're going to cube that, divided by the concentration of the ammonia, and we're going to square that one. In the second example, solids are not included. So my equilibrium expression would merely be concentration of H2S, concentration of NH3. Okay. Yep, and that'd be it. So products raised to their coefficients divided by the concentration of the reactants raised to their coefficients. Very straightforward. Now let's calculate it. So calculate the KQ for the following reaction. So we've got everything's a gas. So I'm going to start off by writing out your KQ. That's trivio is your first step. So the concentration of H2O, CO divided by H2 and then CO2. And then I'm just going to plug in the numbers 0.20, 0.30, 0.40, 0.40. And you do that and you'll get 0.38. Important to note, there are no units for K, okay? So what happens when an equilibrium has been disturbed by changing concentrations and a new equilibrium needs to be established? In order to do these calculations, we have to use a Rice table. Okay, R-I-C-E. Some people call these ice tables and they just leave the R off. It doesn't matter, it's the same thing. So the R stands for the reaction, which you write the balanced equation. The I is the initial, and that would be concentration. And it's important to note that this is concentration. Sometimes you'll be given moles and a volume, and you have to turn it into concentration. C is the change, which is based off of the balanced equation. And then E is your equilibrium. And to get that, you combine I and C. Okay, so let's do one. I think we're going to do two. Okay, so we are going to calculate the equilibrium concentrations for the decomposition of nitrogen monoxide. So I'm going to stop there and write out my reaction, the decomposition of nitrogen monoxide. Two there. Okay, the KQ is 2.5 times 10 to the negative fifth at 1700 Kelvin. A 0.0150 mole sample of nitrogen monoxide is placed in a 12-liter flask and heated. So this is what I'm talking about here. So when I do my I actually have to do 0.0150 moles divided by 12.0 liters to give me my concentration, which is 1.25 times 10 to the negative third. We have none of this. The change is based off of your balanced equation. So I have only reactants, no products, so the reaction will shift to the right, which means I'm going to lose the reactants and gain products. How much do I lose? Well, I'm going to lose 2x because of the coefficient. I'm going to gain x and I'm going to gain x. So what we're going to end up doing is solving for x so we can determine what these concentrations are at equilibrium. So equilibrium, I said all you do is combine I and C. Okay. So next step, write out your KQ expression. Okay. Now I'm going to plug in my equilibrium numbers into my equilibrium expression. So it's going to be x times x on the top. And on the bottom, it's going to be 1.25 times 10 to the negative third. Now this minus 2x, we can actually neglect it. Okay. So we're going to neglect this because it is going to be basically not even change this number here because my KEQ is so small, it's going to be negligible. We're going to neglect it. We're not going to worry about it. Plus, we're not going to do any quadratics. So if you see something that's a quadratic, you've done something wrong. Oh, I did something wrong here. I forgot to square it. So I'm going to square this. Because in reality, it would be 1.25 times 10 to the negative third minus 2x, and then I have to square it, which would give me a quadratic. We're not doing quadratics. We do not have to worry about that. Plus, we'll actually come to find out that the change is going to be extremely small, that number, let's just do it and then we'll see what the number is. And that will be equal to my KEQ, which was 2.5 times 10 to the negative fifth. Okay, so the next step to make this math easier, I'm going to do this. I'm going to erase that, and I'm just going to write x squared. Because that just lets me see here, okay, I can square root this whole side, and then if I square that side, I have to square root that side, I have to square root the other side. So that gives me x over 1.25 times 10 to the negative third, just got rid of all those squares, is equal to 5.0 times 10 to the negative third. And so x, which equals the concentration of the nitrogen at equilibrium and the concentration of the oxygen at equilibrium, will be 6.3 times 10 to the negative sixth molar. So what we want to do for our equilibrium concentration of the NO, what I do is I'm now going to plug that X into here. So 1.25 times 10 to the negative third minus 2 times 6.3 times 10 to the negative sixth. And what that gives me, I'm going to just write it up here. 1.24 times 10 to the negative third. So it barely changes anything, okay? So that's why we're actually able to neglect it when we do our calculation, though we do have to go back and put it in to get our final equilibrium concentration of the nitrogen monoxide. And the great thing about rice tables and equilibrium problems like this is they're all done the same way each time, okay? They all have the same steps. So let's do one more, and then we'll be finished for these notes, and you'll have time to practice because this is one of those things that you'll get better at the more you do. So when hydrogen iodide is placed in a closed container, it will decompose into its elements and an equilibrium will be established. I'm going to try to make this one look nicer because I don't have as much space. My balanced equation. If the initial concentration of hydrogen iodide is 0.025 molar and the Kc, okay, that's different because we were doing KEQ. Well, Kc just stands for concentration. So the you could do, it could be Kc, KEQ, it could be Kp for pressures, but it's all done the same way, no matter what that little subscript is. We're going to see maybe in the next notes, I think, that it's going to be KSP for solubility. So it's just telling you, okay, if I'm KEQ, that's a general statement. If I'm Kc, that's asking for concentrations. Kp would be pressures. KSP, we'll come to find out, like I said, is going to be for solubility. So my I is 0.025 molar, 0 and 0. My change is minus 2x plus x plus x. Now I know both of these were minus 2x plus x, but they're not all like that. So again, what we're going to end up doing is we're going to neglect the minus 2x when we go and solve for x, but we cannot neglect it in our E step because when we go back to solve for those equilibrium concentrations, then we still need to do this. So let's see, my Kc, which is 2.2 times 10 to the negative third, iodine, hydrogen, Hi squared, which is x squared over 0.025 squared, square root this, square root this. I'm just going to skip a couple of steps here. X, which will equal the concentration of the hydrogen, which will equal the concentration of the iodine, is going to be 1.2 times 10 to the negative third molar. Now, this question is just asking what's the change in concentration. So that would be the change. But I'm going to go ahead and solve for the hydrogen iodide. Again, we're going to do 0.025 minus 2x, which ends up giving me 0.023 molar. See, barely changing. That's why we're able to, again, neglect that minus 2x. Now, I'm going to erase this because I have to scroll down a little bit. What do you think you would have to do if you were given initial concentrations of all the species in the reaction, that is both reactants and products? How do I know if I'll be going and gaining products or losing products? That's what we're going to look at Q, which is called the reaction quotient. So what is Q? Q just tells me where I am in the reaction. So if K is greater than Q, the reactants are favored and I'm going to lose products. If K is less than Q, the products are favored, so I lose reactants. And if K is equal to Q, the reaction is at equilibrium. You need to know this. There are going to be multiple choice questions that are merely asking you a question like that. So make sure you understand that concept. How do you find Q? Q is K when you're not at equilibrium. So K is when you're at equilibrium. Q is when you're not at equilibrium. And it's the same thing, Q, concentration of their products to their coefficients divided by the concentration of the reactants to their coefficients. Okay, so you're going to see probably, I think in the homework assignment, there is a question where you are given like this, and you have to just determine, and what it does is it does the change. So it could either be minus x plus x plus x, or plus x minus x minus x. So if like it was, like if we were doing, I know that's not balanced. So it would be like this. I'm making this more complicated than I needed to. So like when you determine your K, your Q, it's going to help me, okay, I'm given everything. I know this, and I know this when I start. Okay, is it going to be shifting to the left? Is it going to be shifting to the right? Am I making reactants? Am I making product? What's being lost? What's being gained? That's what the Q will help you determine. So please make sure that you're working on your practice, because we're going to use rice tables in another context later on in this module. Okay, so the module when we get into acids and bases, that part we're still going to use those rice tables. So it's very important that we have an understanding of how they work now. So make sure you work on that practice for the homework assignment. If you have any questions, please make sure you ask, and I will see you later.